Hello, ladies and gentlemen. Hopefully you can hear me and there are no noises from last time. I will be very grateful for any feedback on the chat regarding audio quality, and I think we can start in a moment. Okay, let's start. Okay, dear ladies and gentlemen, my name is Jerzy Baranowski. Welcome to our second lecture from the Data Analytics course, and we'll be discussing Bayesian basics in this lecture in order to put us in a proper framework for understanding what's going on in Bayesian computation and Bayesian statistics. Today will be easier aspects, and next week maybe we'll discuss how Monte Carlo computation works. So without much further ado, let's start with the also I wanted to mention that I've tried to improve the audio quality. I tried to improve the streaming quality, so it should be in full HD, and it's not. I am sorry. I will try to work it again. I don't have much experience with OBS, so this is a learning process for me also. Either way, let's start with the Bayesian basics. As mentioned before, we follow something called Bayes' rule. Bayes' rule is the fundamental theorem of Bayesian computation, not by itself itself's mathematical form, which, as I've mentioned last time, is a very easy form coming directly from the formula for probability of object probability, but generally it's philosophy. It's philosophy that our prior knowledge together with observed data give us new information about underlying phenomena. So we have prior knowledge about a phenomena, or usually a parameter or vector of parameters called theta. We have data which represents how well our model, our theta, fits the measurements of y. Probably most of people are Polish, actually. I was responding to the chat, and this multiplication of this likelihood function, which corresponds to how model fits the data, gives us information what about the model or what about our understanding of phenomena can be extracted from those observed data. And this is a very basic relationship. However, it is very fundamental in understanding of how statistics works and how inference works, because it's a natural additive process of adding new information in order to create our understanding of phenomena, and this understanding can be again used in future as a prior information with new data. So having that, what we can say, Bayesian statistics allows us to create predictions, because knowing the probability of certain phenomena, we can then create the computation from so-called prior predictive distributions. So we can predict actually how the data would behave considering our prior knowledge. And here we encounter something that we'll be encountering a lot of times, that is integration. Integration or marginalization is a process that will allow us to remove the certain parameters from our model that we are not interested in. And this is very good situation for us, because our models will have a lot of parameters. Those parameters will be either observable or unobservable. and only some of the unobservable parameters will be of interest for us. Because generally, in our inference, we are interested in a certain aspect of a process or situation. For example, we want to extract information about certain value. However, all the measurements and all the process are corresponding to multiple parameters that are happening in inside. So, like for example, we want to analyze temperature inside house, but it's influenced by temperature in multiple rooms and the temperature in the outside of the house, and we are not interested in those parameters. We're interested in one concrete temperature, and that's why we want to remove all those parameters. And generally, in Bayesian statistics, we'll be doing stuff like that. And now we are discussing something called prior predictions. Prior predictions are a great tool for finding out what can we expect having our knowledge. And idea for obtaining probability distribution, because everything here we discussed, as mentioned last time, is probability distribution. We want to have a probability distribution of what the values of measurements will be, why our measurements. And generally, both parameters and measurements have their own some kind of probability distribution that comes from our model, our understanding of situation. And we not necessarily know the parameters of theta, we only have some kind of prior knowledge about them, we have some kind of distribution. And using formula for joint probability, we can of course replace this. So generally, we have this first two problem of marginalization. We have measurements and we have parameters, and both of them have some kind of probability of happening. There's a joint probability that model will have this set of parameters and will produce these measurements, which is kind of obvious. Yeah, like for example, when the heating source is can have certain certain values, then of course the temperatures measured also will have certain values, and of course, depending on the heat, the probability of measured temperature will change. And so this joint probability has certain variables that we are interested in, measurements, and certain variables which are at the moment we are not interested in, parameters. We want to just find out what expected, what is the probability of certain measurement values. Using the formula for probability of joint distribution, of joint probability, we have the integral of prior knowledge times the likelihood dependent on theta, and we integrate it all over theta. So this is a function of theta, this is a function of y and theta, and integrating it by theta over the entire domain of theta, which usually is all the areas where p of from theta is not 0, because if p of theta is unbounded, then we will have to integrate over all possible values of theta. If p of theta is bounded, or not bounded, but has a bounded domain, then, like for example, is limited to an interval, then this integral will be limited also to that interval, because outside of it, it will be 0. So, having that, we integrate over all possible values of theta, and because of that, the function of two variables becomes a function of one variable, which we are interested in, so we get the probability distribution. And we call it prior predicted distribution because it is a distribution that gives us possibility to drawing random values from this distribution, gives us the possibility of, gives us the probable values of y. So give us predictions. And those predictions are based on our initial, or only on our prior knowledge, because we don't have any y here. Y is a variable. It's not data, it's variable. So integrating over this, we'll just have a function of one variable which corresponds to probability of certain values of y. If y is a vector, it's more complicated, but generally the idea stays the same. On the other hand, we have something called posterior predictive distribution. And posterior predictive distribution is the situation when we want to predict values of y knowing the data. This is our actual prediction tool. Prior predictive distribution is used for understanding the model, of having information how the model behaves through how our tool for verification of our assumptions. Posterior predictive distribution is a tool for actual predicting certain values and works almost the same. The main idea is that we want to create a probability of values of y. So what values can we expect having observed already values of y? So this is posterior predictive distribution because it uses data. And the idea is again very, very similar to the previous one, because the probability of our we have a joint probability of y with tilde and theta, which is now just conditional on y. So it's a joint conditional probability. Joint of these two variables, conditional on observed variables. So we know that we've seen those y's. So what can we know? How did it influence our situation? And this again is something that we have from the we can again use the appropriate theorems, and this again will help us drastically. Why? Because we can now use the probability of formula for joint probability when we can divide this the probability of y with tilde as being conditional on both theta and y, and times the probability of theta conditional on measurements. Probability of theta conditional measurements is something that we can get from Bayes' theorem, so we'll be able to input it here. And probability of y conditional on theta is now much simpler situation, because having the direct values of y are corresponding to parameters is a likelihood function, which does not directly include the measurements, because under certain standard assumptions, exactly, y is the prediction, y with tilde is prediction, y is the measurement. So y exists, y with tilde is something that we want to get, or we want to infer. So what will happen? That's what. So generally, if our problem is not a time series, we don't have the basic causal relationship between tilde, y tilde and y, but we have this joint relationships between parameters. So this relationship really is that parameters generate value of y, y tilde. So this here will be our likelihood, the likelihood function that we had previously before, and we will be able again to integrate theta out of it, the same like it was in the prior predictive distribution. So this is just a situation that we can, so this part here, and this part. So we do not have the need of having y here, so we can drop it, because this relationship does not exist in this causal relation. It is more in this probability relationship we have with. The measurements are independent. The predictions are not directly dependent on measurements, just by the dependence of parameters on the conditioning of parameters on values of y. So this is a very similar formula: likelihood and knowledge about theta. But this knowledge about theta is, of course, this knowledge about theta is conditional on y, and we can get it from the Bayes' theorem. So we can replace this formula here with likelihood of y, not tilde, but y on theta. So we will, y at the moment is not a variable, it's a number or a vector of numbers or a general data set, and probability of theta, so the initial probability. And maybe I'll come back to this for a second. So prior and posterior predictive distributions give us this, knowing the data, give us the information how to generate possible values of measurements, either not seeing any measurements before, just basing on our knowledge, or how the obtained measurements give us the predictions of future values. And fortunately, those formulas won't be almost ever used directly, because these formulas are very complicated whenever theta stops being a number and it becomes a vector. And in almost all real problems, theta will be a vector because all problems have multiple parameters. So fortunately, Monte Carlo computation will allow us to solve this issue by actually computing certain expectation of probabilities. So both prior predictive and posterior predictive will be computed by simulation, not by and not by the integration, and by the fact we won't have the formulas for prior and posterior predictive distribution. We will just have samples from those distributions. So we will be obtaining the predictions directly. We won't be obtaining the probability distribution, but the prediction from that probability distribution. So generally, prediction from a probability distribution will be just a random vector sampled from this distribution. Hopefully it's relatively clear. What we need to know, additional aspects of notation. First of all, generally, we might not be writing it all, but every probability is conditional in Bayesian framework, because every probability assignment that we have is conditional on certain knowledge that we have. For example, if we want to make a coin flip and we want to assign the probability of heads or tails, this really is a matter of having the information that the coin has two sides. And this coin not necessarily has two sides, because it also has the edge of non-negligible width. So it is possible that our coin will be standing on its edge. I probably won't be able to do it because I have to stabilize two things at the same time. But the point is here. When we assigned equal probabilities of heads and tails, and we assign negligible probability to the edge, because it happens rarely, then we have actually the knowledge about the shape of the coin and some experience of throwing it. If, however, for example, we were on Mars and we've heard, oh, there's an item called coin, and we can flip the coin and we can get heads or tails or edge, which is, to us as a citizen of Mars, an abstract concept, because we don't have idea what a head or tails or edge is, because we don't know English language, we know Martian language, and we haven't seen the coin before because we are communicating over, let's say, space chat, and we want to assign the probabilities to well, there's an item of chance, and it has, let's say that we understand probability as a common language of the universe, because why not? And there's an item called coin, and we have, it's a three options, heads, tails, or edge. So we, as a Martian, we said, okay, here is a probability object, so, and here you can throw it, three options, so we get 1/3 probability of that. And both assignments are conditional on our state of knowledge. If we've seen the coin, our state of knowledge is how the shape is assigned. there is no such thing, or almost no such thing, as objective assignment, such situation that is conditional on nothing. Because in every situation we have certain assumptions, idealizing assumptions that are removing this conditioning, but very often we just don't discuss it because certain, just in order to, because we don't use those assumptions too much, or they are common for the entire model, and they just clutter our notation. But generally, everything is conditional on something and some kind of information that we have. We all have two very important functions, that is expectation and variance of probability distribution, which you of course should know. Expectation is an integral on the first moment of this distribution. When you just compute the integral of the distribution of parameter u, multiply as an integral of this function p from u multiplied by u over du, and variance is, well, this is the expectation of certain function, because generally we will be computing expectation of certain functions, of certain random variables. And again, fortunately, we won't need to do it by integration directly. We will be using Monte Carlo simulation in order to get our results more clearly. Following that, we have, of course, the idea of conditional expectations, because they are, which kind of might be used in certain situations, because again, we will have to compute the expectations over with the same rules. That is, if we want to compute an expectation of certain value, we will just need to compute expectation of a condition of an expectation of conditional distribution. So we have double integrals, and because of that, by appropriate movement of variables, we will be able to just reduce our problem to computing expectation of certain function here. And the same rule appears with the variance, which of course, I have here unmatching parentheses, sorry. The variable here is we have variance of u will be a sum of expectation of a variance and a variance of the expectation. Generally, this is something that we might use in certain specific situation, but it's more of the idea that's going on, that there are functions that we are just computing certain expectation. And computing expectation is useful because expectation usually we can compute by averaging, and averaging is a very important tool when you are working with samples, which we will be doing. The things that we'll be also be doing is changing variables, and changing variables is something that it is very important for any kind of computation because of multiple reasons. Usually because we want to get we want to get certain values which are not directly represented. They might be represented by a combination of different variables or as a function of certain variables. For example, in certain aspect of crystallography, we can measure certain values which are a square of quantity of interest. They are not actual value, but we are interested in the square root of the thing that we've measured. And the problem is that with large noises, the square root can behave specifically. So because of that situation, we cannot use it directly. We need to do some certain considerations. So we can need to, for example, assign the probability of what would the square root value will be. And depending on the kind of distributions that we are making, so it's either discrete or continuous distribution, situation might be more complicated. When changing variables of discrete distribution that is, for example, we have limited option or discrete positions of variables that we can compute the. So generally we have a limited options that we need to assign the probability to. Then it's much easier. We just assign the probability of to the inverse function. in case of continuous distribution, we have the issue that integrals and derivatives have to hold. So in such situation, change of variables requires from us also adding the Jacobian, so the determinant of the Jacobi matrix of the transformation here. Jacobi matrix, that is a matrix of first partial derivatives. If it's a scalar distribution, it's just the absolute value of the derivative, which we need to multiply our computation here. Generally, this is used for situations when the variable, because in continuous functions there can be situations that much but very thin areas are contributing to a lot of probability. Because remember, probability distribution has to integrate to 1. The integral of a probability distribution independence of dimension is equal to 1, because probability of getting a value from this distribution that is just some value that is possible in this distribution is 1, because that's only that we have. If we have some bounds on it, then we need to compute the integral over certain area. Probability of finding of one particular value of continuous distribution is always 0, because again this is one point under the entire infinite area under the probability distribution. Infinite, that is, has infinite many points. So 1 point to infinite points is 0 probability. So probability is generally the area under the curve of probability distribution. And in case if we want to change the variables, we need to switch the shape of the entire distribution, and such shift must preserve that integral of the entirety must be equal to 1. That's why we need to introduce this part. And generally, we will be using variable changes. We'll be using variable changes very often in computation because it's the only way to efficiently keep the variables contained. For example, when we are working with our variable of interest is only positive, and we want to compute certain aspects of it from, let's say, linear combination of variables, we introduce the logarithmic transformation. Logarithmic transformations will switch allows us transformation from 0 to infinity to the entire area from minus to plus infinity, because logarithmic function takes arguments from from the positive reals and returns values from minus infinity from all reals. So all real values are obtained by a function from 0 to infinity. In case of in case of when we have the aspects from bounded intervals like 0 to 1, or generally bounded, very useful is logistic transformation. Logistic transformation allows us to transform from 0 to 1 to minus plus infinity, or using inverse logic transform inversely. This is very useful, especially for situations when, for example, we want to predict the probability of something, because we won't have values between 0 and 1, and our predictors have different values, and in such situation we have used this transformation that will just squeeze the entire real axis into a 0-1 interval, and this is just kind of sort of sigmoid function. Similar function is the probit function, the function that generally works like an inverse cumulative distribution function, because it transfers the it works between 0-1 interval and the interval of minus plus infinity, like a Gaussian distribution assigns such probabilities. With the cumulative distribution function is a kind of sigmoid function that gets us to the that starts from 0 and goes up to 1, covering as much area as you can. Both logistic and logit and probit transformations are useful in classification, probability estimation. The main difference in using them is the tails, because logit has more importance also to the values farther from the middle of interval, and probit is more, the farther the values, the flatter the tails are. So the larger values contribute less to the actual value between 0 and 1. Logistic function is more gives more influence of the aspect from 0 to 1. Generally because one behaves like exponential and other behaves like a Gaussian, so an a squared exponential. Okay, so giving that initial framework of what are the prior predictive and what is the prior predictive distribution, what is the posterior predictive distribution, what are the expectations, how to compute those expectations conditionally and not conditionally, at least on the conceptual level of integrals, and introducing the changes of variables, we can now discuss something very simple: single parameter models. Single parameter models are generally something that at first glance seems useful to us, because it's not useful to us because really we want to have complicated models that will predict, for example, stock market behaviors, or COVID patient prevalence, or whatever else, but like the complicated aspect. But in practice, single parameter models will be used as building blocks of more complicated models for assignment priors or likelihoods for individual parameters in those models, and also to answering the very simple questions which we reach after certain transformations. So for example, what is the average difference between two groups, or what is the strong association, but how strong the association, for example, linear association between the treatment variable or just the variable that we are modifying on the outcome. So how is this relationship, how strong is the relationship? Or we just want to verify, is the effect dependent on certain additional covariate, additional variable that we have, or not, or even we want to know how much is the variation between the groups. So how much are different, how much spread is in each group. So we want to estimate those values, and for that we will be using those single parameter models. And the easiest single parameter model to use that we want to have is the binomial model. Binomial model, that comes back to the issue of flipping a coin. So what is the difference of generally n-exchangeable trials? Exchangeable means that variable is exchangeable if it is we don't really care of the order how it's happening. We don't really care how they are grouped each other. We just know that each experiment is exchangeable if within certain group we don't really care the order or sequence of those experiments. We might have a situation that there's a partial exchangeability. Like for example, we have an experiment in which we switch the we have an experiment that the order of experiments matters, but not but by itself the groups, for example, we don't care which of the experiments we are analyzing, but we care how the samples during the experiment were connected. So for example, we measure the time series, and time series, like for example an experiment on the laboratory system, we've just measured how our controller works, and we are very interested what was the transition process from start to the end, but we won't care to creating the parameter estimation model or the evaluation model which of the experiments happened first, because we have a sequence of experiments on different days on the same controller without any possible changes, and then we can exchange them. This is exchangeability, partial exchangeability, because so not every data point is changeable, but the groups of data points, so that time series data points, for example, are exchangeable between each other. And in a binomial model, we have very simple situations of the exchange of the trials or events that have binary results. Those binary outcomes are usually described as success or failure because it describes either something happened or didn't. And this is our model. This probability of this success, of course, is described by theta. So, in case of knowing theta, the probability of y, so the number of successes, is equal to the formula given here, which is the probability of, of course, y successes in n trials, is that scaling Newton factor times the probability of success up to y times 1 minus the probability of success to the rest of the trials. So it all depends on the number of trials and the number of the probability of success in a single trial. And this is a very nice example, which unfortunately we cannot replicate now. Here in last year I've did it on lecture. I just brought a rubber globe, and that we were throwing around a classroom and catching it. So it was a bit of active fun. Generally, imagine Mass Effect 2. I'm not sure how many of you played Mass Effect 2, but in Mass Effect 2, I'm not sure about Mass Effect 3 really, but in Mass Effect 2 there was a situation that you were, Normandy was flying over the planet, and you were dropping a probe on the planet's surface. And depending on the probe, you got the results of what was being collected from it. So we are considering a planet, we are dropping a probe, and that probe finds us either there is a water there or not. We want to estimate what coverage of the planet is water. So we know that dropping a probe on the water on the planet will give us either a result of water or land. Probability of water is p. Probability of land is 1 minus p. Because let us assume that planet is spinning relatively fast. Our flight is not really connected to, is we are dropping random drops on the planet. So with a bit of, let's say, positive thinking, we think that each measurement is independent of each other. So we want to estimate what is the coverage of the planet with water. And because of that, we perform this experiment. For the purpose of this exercise, we will focus on the tossing of the globe with the that we got 7 successes in 11 trials. Because, like, again, on normal lecture, I would just throw a ball around you and we will see what would happen. In this case, we have 7 successes in 11 trials. So we get our likelihood that we described before. Here, this is our likelihood function because it relates our y to theta. So how well our measurements fit with our theta. So our likelihood is just a binomial probability mass function from the stats package in NumPy, and we get we can compute this function for different values of theta, and for this purpose we just go with, we can then plot it and show it here. I will ask you for a bit of let's say patience with me because I've just realized that I haven't rerun this notebook before, so maybe some issues here. Just in case that we don't have anything, I just want to import everything so it will be working. So let's just import all the packages. I'm using here Seaborn package for plotting, but it's not really something that is very needed. That just makes those figures a bit nicer, setting up this dark grid formula, and I just want to be sure that everything will be working. So what I'm using here, I'm using scipy.stats module with imported as stats. I'm using NumPy imported NP. I'm using Seaborn imported by SNS, and I'm using the matplotlib pyplot as PLT. For this purpose, I'm assigning values of theta as linear values between 0 and 1 in 200 points, so it will look possibly nicely, and I'm using the of course I'm plotting it and using the dark grid Seaborn style to get these more nice plots here. Generally this is the main use of Seaborn, just to set up the styles and then you just do everything in Matplotlib. But again, if Seaborn is a bonus here, I won't be using it that much in further lectures because this is something that is left in. I'm using Rise for lectures here to convert the Jupyter notebook into slides. It is the based on Reveal.js, so it's a JavaScript realization of the notebook. So we've plotted here this likelihood. This likelihood looks like this, and this gives us certain information already. As you can see, this is likelihood. Likelihood is not necessarily normalized. In this case, it is, but this integral is not necessarily equal to 1 because it all depends on the scaling factors, which we can drop on that. Okay, so let's focus on how the likelihood, how the situation look in here. We are focusing on a situation that we have no prior knowledge about theta. So we just assume that theta can take any value except the fact that it's a value between 0 and 1 because that's where likelihood holds. So in this case, posterior is up to a scaling factor proportionally equal to the prior. So they are equal to the likelihood. Likelihood decides about everything because setting not using any knowledge about the theta, we assign that is constant probability for all of values between 0 and 1. So in this case, the probability will be the probability of a particular value. This will be just multiplication by constant. In this case, we had a binomial distribution that relates the y to theta, because in creation of posterior distributions, we really have a very curious situation that likelihood is a function of y dependent on parameters theta, but it has a formula that presents both theta and y. So it represents as information how y fits parameters theta, which are governed by additionally by the potential prior distribution if in a posterior. However, when we start considering as a prior, posterior, nothing really changes. The formula is the same, but our interpretation changes. Because now we look at it as a function of parameter theta dependent on fixed values of y. In construction of the formula for posterior distribution, we used formulas having letters in it. And now we look at different interpretation of those letters. So binomial distribution, probability of y given theta, is now changed into the probability of theta given y, which is now a beta distribution, because the distribution of parameter of theta. The main difference is that binomial probability is number probability of successes for y's which are integers. Beta, on the other hand, is the probability of theta, which is a value between 0 and 1. So it has different domains. The fact, without, despite the fact that we were kind of looking at it as we haven't changed the formula, but the domain is different. Y is considered a parameter because we've measured how many successes we have, and theta is a variable. So this function here is the beta distribution with coefficients y plus 1 and n minus y plus 1. So this situation is relatively simple, and but needs a certain different look on the situation. Could you please tell me, were there any issues with the stream? Because my YouTube studio started behaving wonky, so I wanted to ask, are there any issues happening? Please, I will wait for a moment till we get on chat, and I'm waiting for some kind of answers from you. Okay, let's have for a second. Is everything working? Please let me know. That OBS is disconnected. Now it's connected again. Like everything is weird. Okay. So so to restate this fact, the posterior distribution changes the look on the formula. Formula looks the same, but interpretation of this formula is different because it's the formula for different variables. Okay, so we have the posterior because we've managed to get it previously. We've managed to plot it. What can we do with it now? Because we are interested, what is the value of theta? Bad news is the posterior does not give us information what is the value of theta, only gives us the probability distribution of that. Why is that? Because provided information is not precise enough to give us precise answer. And really, because this provided is only the process. The process is that we've observed that in 11 trials, we've observed water 7 times. And that's it. That's we know. This is not, this is give us certain uncertainty about it. Why? Because it is possible that with some random chance, we've dropped on our probe only into a single pool that is very limited on the cover of the entire planet, and we've measured that water. This is a very low probability, but it's possible that our measurements were very badly behaved. So it is possible that we got results from somewhere here. So for example, that there is almost no water, but we've dropped it into someone's swimming pool multiple times. It's a very low probability, but again, it is potentially possible. So what we have here? We have a distribution. This distribution is, of course, most of this mass, the probability is located somewhere between 0.4 and 0.8. But we need to summarize our information, and well, it depends on kind of distribution that we have. Generally, posterior distribution is the best summary of itself because you give all the information. For example, for student surveys that we are currently doing all the time at AGH, we have the discrete, very specific distribution because we have results of your surveys are not numeric values, they are ordinal values. What does it mean? It means that generally, most of you won't be representing your grade of the teacher as a metric way of saying that you like them in 80%. Then you have the question that you like
you have a statement and you agreed very much, generally agree, don't have an opinion, generally disagree, strongly disagree. These are not numeric values. You cannot say that variable that I agree very much, which is marked as 5, and agree somewhat agree, is 4, is the difference of 20%. It might be a very strong difference, depending on a person. This is an ordinal value. We know that somewhat is less than fully agree, and somewhat is more than neutral. Somewhat agree is more than neutral, but besides that, we don't know. So the best summary for a decision maker or someone that wants to evaluate this teacher would be the entire distribution. So you will see, okay, generally people agree with this description of the class, but there are some separate people that have different opinions, and those changes are, for example, the same balance of situation when you have the differences in scales might be the same values might get completely different representation. This is not a metric value that you can average and get some kind of average, because, for example, you can average out of, for example, someone's presence in classes. Let's say that the classes happened in 80%. This you can measure. This is a measurable value. This is a metric value. But you cannot metrically evaluate teaching style based on such given situations. So only a distribution evaluation would give you some kind of insight of how this person is teaching, not the
general average. So in many situations, entire posterior will be the best, but we are not very good at looking at posteriors, especially more complicated ones. We don't think in the scope of RES. We just look at the maximum value, and this maximum value can be strongly misleading, which we'll talk maybe in the next lecture. And we look for some kind of, and we want a number that we can put our decision on. So usually we use something that is the most central point or something. So popular is mean. So we have the mean of the posterior, the expected value of the posterior. Or we have median, so the point on which 50% is less, value of having less value is either 50% lower or 50% and higher is also 50%. So it's exactly in the middle of a trial. Or mode, so it's the point that is most natural when we're looking, but not necessarily that informative. That is the maximal value. The maximal value for probability is something that we can use with that. And this is a number that gives you kind of information. However, if it would be very thin, this mode not necessarily would be very good, especially if it would be, or if especially if it would be very wide, the mode would give you not very much. It would be very thin, mode would be good representation of the most of the mass. If, however, it would be very wide, very flat distribution, the mode would say you really nothing. So, having that, we would also love to add some other some information about the variability of the parameters. And for that, we need to add some other parametric values. So, for example, the most typical way is to use standard deviation. Mean plus standard deviation relates us to the normal distribution. If a distribution is somewhat normal-like, then we can add the using the standard deviation. We know that, or you should know that probability distribution, that the probability of value lying between mean minus standard deviation and mean plus standard deviation is 67%. Mean minus 2 standard deviation to mean plus 2 standard deviation is 95%, and mean minus 3 standard deviations and mean plus 3 standard deviation is 99%. So you have these, you should know the areas, and usually when you find, for example, some data in medical data or vote data, usually this scheme is used. When they give you
plus minus something, it is usually one standard deviation. So for example, when you are looking at election predictions, this is one standard deviation. When you are looking at central grids for your children, and it gives you what are the intervals here, this is a one standard deviation. So, going from that, other options, quantiles. Quantiles are more robust in certain way because they'll just give you what is the probability. For example, what value is larger than 90% of possible values, for example. So probability that something is smaller than 90 value for under which 90% of measurements will be smaller than, or value under which 5% will be smaller than. So you can use the either interquantile range, so the spread between 25% quantile and 75% quantile. So the median plus minus 25%. Those values, this is an interquartile range, and it will give you some kind of spread. Also, you can just use other quantile ranges, or just give you the quantile values. So you, for example, have information about asymmetry. Why? Because having quantiles, well, having mean and standard deviation, there is an assumption of symmetry. If there's an asymmetric distribution, it might be that certain, for example, 75% quantile will be much closer to the value of median because the probability distribution will be asymmetric, it will be skewed. Like it's more flat on one side and much more steep on the other side. So this will give you some interpretation. So that's why quantiles are very often very nice option of summarizing the probability distribution. Generally, the problem is that we really like numbers. Less numbers, the better, and it's not necessarily that good situation. Because, for example, we want to use something called interval summaries. Interval summaries is that we want to give, for example, a 95% confidence interval. So that's the interval that the parameter lies in this interval for 95%. We know that we cannot use standard deviations because of the asymmetry and stuff like that. And we cannot use the quantiles because we want more precision. So we want to just know what are two values that contain the median and has, or symmetrically represents that you have the 95%. And you get those values. You compute them numerically from the obtained probability distribution. Or you can use highest posterior density region. So you can find the smallest interval that contains, for example, 89% of probability. So you can, again, numerically compute that. The problem with those intervals is that if the distribution is not unimodal, is more complicated, like here, you can have a situation that such interval is too wide because it does not represent these issues. The problems with those issues is, for example, the most known one is the average pay in Poland or in other countries. The average pay is that the average national salary is much higher that most people earn, because there is a two-modal distribution. There's a large mode of people who earn very little and a small mode of people that earn much more, and a thick tail of people that can also earn a lot and just skew this distribution. This causes the situation that people have that people do not have the enough that people do not have that having this interval summary does not give you information. The mean value is absolutely misleading. Mean value is located between two modes and nobody earns that much money, for example. And the worst case in interval summary is that there can be even disjoints, that there are two intervals give you the entire probability and you don't have so all summaries have their flaws. The best thing about this situation is that summaries of that the best option would be providing posterior, but for multi-parameter situations is bad. The problem generally with multi-parameters is terrible with summaries because usually we have to look at the marginal distributions, and marginal distributions are very difficult to interpret and spread into numerical values. We'll discuss that later. Okay, so let's go to priors. Generally, priors can have two interpretations. Because the main problem, again, with Bayesian statistics is the philosophy. We do not have the philosophical representation of consistency between Bayesian approach and frequentist approach, and people try to think how this the you can interpret. So, in population interpretation, it is much easier to handle for frequentist approach because it's more somewhat objective in certain situations. Because population interpretation gives us that prior list represents the population of possible parameter values that theta can come from. So, for example, the best example is the age structure of the society. If we have we have measured our entire society, so we can assign a distribution, even discrete distribution, that represents probability of certain person to be this age in this with the precision up to 1 year. So we can get that from the General Statistic Bureau of Poland, and we get we have the population representation of our entire population. So we can then assign what is the probability of the age of a person. For example, this is simple and does not raise much controversy in this prior, that we have certain general information about the population that we are interested in. This population can be, for example, looking for, let's say, assignment of certain production, manufacturing. We know that what is the quality control behavior, so we can assign probability that how much of equipment will not pass the quality control, and again, behaving on the population of multiple things. The more difficult interpretation is the state of knowledge. In a situation that we do not have a population, because, for example, situation is unique. We do not have an experience that we can draw. We do not have the broader field of multiple repeatable situations. And we must express our knowledge about parameters that we know something about, but not really much. And here, not exactly, because and here, for example, we really need to think that theta, the parameter theta, is not random, but from our state of knowledge, it could be any of these values that we have with probabilities like this. So this is our interpretation, that, well, from our experience, our observation of this machine, we know that this parameter should lie in the interval of 0 to 20, and it is impossible to be lower than 0, but it's possible that it's like 10% situations that we've encountered when measuring it good higher, but like we've heard that it can go even higher, but it's very rare, and something like that. So we got this situation. Of course, I'm presenting here very unprecise situation of discussing with an expert. In some situation we have the much more we have better insights of what's going on, and sometimes we just want to give some kind of regularization to our situation, which will again highlight maybe next lecture. And generally we just mean that despite the fact that this is not a population of repeatable situation, of a population of possible parameters, values of possible realization of the process, we just have the certain assignment of probability of this parameter, which comes from knowledge of uncertainty,
and that's it. And our state of knowledge can be represented as a probability distribution. And we have multiple kind of priors because the independent of fact of our interpretation, we can generally have the informative priors, which are useful because we want to introduce new information to the process. For example, value below 0 is not possible. For example, it comes from previous experiments. We did some experiments, we know some stuff, so we want to use that stuff in order to improve our inferences. For example, in case of binomial example, we can use just a beta distribution that we know that previously we had alpha minus 1 successes and beta minus 1 prior failures. So having that, we can just add additional prior of what we knew before. So this is a very nice situation of which we will highlight in a moment, which is called conjugacy. In case of a posterior with informative prior, it's in this case it even has a closed form because both likelihood and prior has a form that after a multiplication behaves like a beta distribution. So it is the we can get the closed formula for probability of theta, which depends on both previous measurements and new measurements. So previously we have alpha minus 1, if I remember correctly, sorry. Yes, we have alpha minus 1 successes and beta minus 1 failures, and this time we have y successes and minus y, minus 1 y failures. So we get this new beta distribution of probability for theta, which can even, knowing beta distribution, we can compute it expectation. And what is actually important to observe here, and what we can get here, that the mean or the expectation of the distribution always lies between the sample proportion, so y divided by n, and the prior mean alpha divided by alpha plus beta. Because in this case, posterior is actually some kind of weighting of or a combination of both data and prior information, which generally makes sense that we can kind of average certain results in the middle. This case that by multiplying prior and posterior, that results in the nice analytic formula, it's called conjugacy. Conjugacy is something like that. If certain probability distribution, which is which will be our posterior, belongs to certain type of functions called with p, and our likelihood belongs to f, while prior also belongs to p. So in other words, when function from f multiplied by function from p results can be transformed by multiplication and interpretation of coefficients into the function from p, then p is conjugate to f. That means that having this prior results as the prior results in the analytically analyzable posterior, and it makes very easy analytical computation and generally benefits end here. This is a similar situation that we had in automatic control with performance indicators of integral of error squared, or we have the situation of linear quadratic optimal control. Those things are very nicely computable and not that useful in practice.
Conjugate distributions lead to simple analytic results which can be computationally very fast. This is great. But in rare situation, conjugate priors are useful because of their properties. The fact that you can compute something analytically does not necessarily mean that it's good. In case of binomials and betas, this is one of the very limited cases that it's good. The same is with normal distributions, because normal distributions are conjugate with normals, and all the rest is very, very problematic, because in order to get your prior to be conjugate, you have to either ignore a lot of information, or you have to add a lot of information that doesn't necessarily make sense. That is the conjugate prior obtained from the posterior will include things that you do not have supported by data or by prior knowledge. You just included them because conjugate said so. And conjugating is not a statistical property, it's just a formulating bonus. So it's using conjugate distribution if they make sense, great. If they don't make sense, look for something else, especially that now we have Monte Carlo computation that solves out those issues relatively well. And let's look on more question of prior influence with an example for biology. There is a phenomena in biology called placenta previa, which in Polish is called łożysko przodujące. Placenta is this part that connects the mother's body to the umbilical cord is something that connects baby to placenta, and placenta is the part of that is connects umbilical cord to woman's body during the pregnancy. And this is effect that after the birth you have to also birth the placenta, so you have to separate from mother's body and be removed usually by doctors. In case of C-section, of course, this is more straightforward. And there is a certain condition called placenta previa, which is caused that the placenta is located first during the birth. So not the baby goes out first, but the placenta goes out first. And there was an investigation of whether the placenta previa is much more prevalent in the female is more present in the female population or in the male population. And so the question was, is the proportion of girls born with placenta previa lower than the proportion of generally girls born at all? So they made a trial with 980 births of placenta previa, 437 of which were female. So we'll do some computation here, which hopefully will work, because I haven't updated Avis here, and Avis started doing strange stuff. So we have our previous computation with uniform prior, and it gives us the posterior of beta with parameter 438 and 544, for which we will compute 10,000 samples, on which we will compute the highest posterior density interval of 94%. What actually are we doing? We are computing samples from a beta distribution. It is again convenient to use analytical formulas because they are implemented by someone, and there's a random number generator that generates values from the beta distribution. So we are sampling the beta distribution, we are computing it in 10,000 points, and then we will be computing the highest posterior density interval. And we do it like this, that we just sort the variables and we find the minimal and maximal value that contains the 94%. So we find that the median is 0.46, so the proportion is like this, and it's contained this asymmetric interval with respect to median, because as you can see, it is more skewed to the right. And probably it will break now. Okay, wait a second, because I want it to be too good for my own options. Okay. Oh, now, so we get this interval. Our probability distribution here is a beta probability distribution with those coefficients, and our highest probability interval is here with median that was not marked here. Maybe I should have marked it. So, as you can see, such computation is relatively straightforward, and this is something that we'll be doing all the time with much more sophisticated tools, but generally we will have a posterior probability distribution created in some way, and we will take samples from this posterior probability distribution. And then, using those samples, we will compute some statistics on it, intervals, values, and from those values we will be getting our inference. So, in case of our probability distribution, because we don't have to use any other tools, we have conjugate prior of beta, and we can actually do something like this. We know that probability of female birth is estimated as 0.485. So we can assign beta distribution in a way as a prior information that just corresponds to previously observed births consistent with our observation. So consistent with general female birth representation. So we know that the mean number of births will be here given, and the population size will be alpha plus beta. So we just can constrain this population size. We just constrain the mean and just modify the population size and see how, in case of our experiment, how our experiment's interpretation compares to the changing previous experience. So we have a bigger experience, we have good prior information, and how this good prior information from varying number of births influences our computation. So again, we will try it with 2, 5, 10, 20, 100, 200, and 1000 previous birth, which we will then compute again this the same situation. We will just compute the highest probability intervals and medians for such situations. So we will just be changing priors. We'll be changing those priors using the analytical formula for posterior just by changing the population size. So we compute the alpha and beta in a proper way. Okay. So without further ado, we can compute this, which will be relatively simple, and we get the again, something was not run by me previously. Okay, I just wanted to put it into the data frame. Okay, now it should work exactly. So charm of rice. Okay, because this is soup slide, something like that. Okay, now we have it. So having our private interval, we can now see that the bigger the population, the median is moving towards the mean of initial computation, and the interval by itself is getting also moved away. With 1000 of births recorded before, we are generally balancing our study. So we have moved from our original prediction more to observe. So including more data that is not consistent with the situation just moves us away from this observation of the likelihood. So prior can keep us away from the from the observation. Why? Because okay, we are observing this, but our previous knowledge said us this. So our observations are not really that consistent with prior knowledge. So we need to think, why is that? Maybe there's something wrong with the study. Maybe something wrong with prior knowledge. But usually the prior knowledge is kind of well motivated and comes from experience. So there might be a reason to investigate why those differences are here. Okay, another figure that I need to generate here. Okay. Okay, and this we can see here with the we can see it here using the graphs. So as you can see, the prior, depending on the population size, becomes less and less diffuse. With uniform prior will be, or almost uniform, will be almost flat and will not introduce much change. The bigger the population, the more confidence we have in that representation of probabilities, and because of that, our posterior will be more and more drifting towards the prior, because prior knowledge is also an important aspect of our analysis. And because it is one, I think that we can really maybe just add the discussion of non-conjugate prior, and we will finish on that. So what is with non-conjugate priors? I'll just run this in the background and let's go back to the slides. Okay, so in case of non-conjugate prior, by setting it, for example, a normal distribution with the studying a normal distribution, we just say that it has a limited variance of probability, which is only for 5%, and we know that this probability is 0.485, so we add a normal probability for the probability of birth, then our likelihood will also move. But this is something that we cannot compute using the analytical formula, because because normal distribution and beta distribution are not conjugate, or in this case binomial distribution are not conjugate. Because of this lack of conjugacy, the analytical formula for expectations, median, stuff like that does not exist. But it can be numerically computed. And this will be end for this for this week. Next week we will move on to methods of analyzing posteriors using multiple different methods, and possibly it will extend to more than one lecture. Okay, are there any questions now? Was everything clear? Everything was legible? Everything is working? Feel free to ask. If there were any technical issues, please let me know. You can also ask me on Teams if you prefer. If situation is that you don't want to ask during lecture, you can send me lectures later. And if those questions later on email or Teams, and I can get them together, make a list of them, and prepare a Q&A video that I will post on the channel, or just include in the next live lecture. If everything is clear, then we will be finishing in the next 1 minute. 1 minute, just to give everybody time to finish. Thank you very much and have a nice day.